Okay, folks, our first topic of the second semester here is chemical kinetics. It says topic 14 down there at the bottom. That does actually coincide with the chapter in your book that we will be in as well. It's chapter 14 in your book. And as we move forward here, before I really get into the specifics of the topic, the first semester is a great base of knowledge for some things that show up on the AP exam, but where you're really going to make a difference in terms of your score on the AP exam is your knowledge and comprehension of these remaining 6 chapters that we will have for this second semester. I believe that as much as 65 or 70% of the exam actually does come from these chapters right here. So I don't want to downplay the first semester, but this is definitely a very important time here as we finish up the rest of this course with these final 6 chapters. So at the top here, it does say what we learned last year, and I don't know for certain if you guys talked about chemical kinetics before. I'm going to assume that you haven't, so just ignore the title of this slide here. But before we really move on, I want to talk about what the word kinetics does actually mean. And it has obviously a lot of meaning outside of the field of chemistry, but in terms of chemistry, what we're talking about kinetics is exactly this right here: how fast a reaction proceeds. Is it a reaction that goes quickly? And an example of a reaction that goes quickly, you can think of like the burning of propane in your grill. That's a reaction that goes very quickly. Unfortunately, you guys don't have a lot of experience with reactions that proceed in a very slow manner, because the types of reactions that you have to be shown as a high school student with only 50 minutes in a lab period, they can't be reactions that take place very slowly. But for example, in pharmaceutical companies, there are reactions that they will leave to run overnight. It's not an instantaneous signal or sign that a reaction is proceeding. It actually does take on the order of hours to complete. This is something that we're going to be able to quantify, and we quantify it with this unit right here, which can be said as molarity per second or moles per liter times second. For the most part, this portion of the unit right here is pretty standard in terms of quantitatively describing the kinetics of a reaction, but the time unit, as I said earlier, we're used to things that happen on the order of seconds. So that's the reason I put that seconds in there. But you got to remember that I said some reactions do take on the order of hours or even minutes. So that time unit can change either into minutes or hours. And the next slide here is going to talk to us about how a reaction actually happens. And we can alter the rate of a reaction if we can manipulate certain factors that are described by the collision theory. So before we talk about manipulating the reaction rate to either make it go faster or slower, what we want to do first of all is remind ourselves, or if this isn't a reminder, to talk a little bit about what the collision theory is. So there are 3 stipulations that have to be met in order for a reaction to take place. So when I talk about a reaction taking place, what I literally mean would be 2 or more reactants making products. Okay, so I don't want to think of a reaction as like the overall balanced chemical equation. I'm literally talking about the physical act of reactants making products. And as I said, there are 3 stipulations that are set forward or put forward by the collision theory in order for reactants to make products. Okay, so the first thing that must happen is a reactant must physically come into contact with another reactant. Okay, so there must be a collision, and hence the name there, between 2 or more reactants. Obviously, a product can't be formed unless there is a physical contact between 2 reactants. And as we move forward with this collision theory here, I'm just going to get more specific on what this collision right here must feature in order to make a reaction. So the first stipulation is 2 reactants must meet. The second stipulation is they have to meet in the correct orientation. So what I'm going to draw here is basically what a lot of biology teachers do for enzymes, okay, with the activation site or whatever you want to call it there. But the two reactants have a specific orientation that must be met in order for the reaction to take place. And what I like to think about it as a lock and key. We all know that there's one specific way that a key fits into a lock. Obviously, there's a specific end, and there's also, if you hold it upside down, we know that that doesn't work either. So if we can talk about, maybe describe it like this, okay, that reaction there is not going to take place. This is the correct orientation. So again, as I move down, I'm going to get more and more specific on what that collision must feature. So not only must they meet, and that's what we described up here in number 1, they have to meet in the correct way. And to make it even more difficult here, to make it more specific going down to the third, not only do they have to meet, not only do they have to meet in the correct way, there has to be enough energy. The collision must be violent enough to overcome what we call the activation energy. Okay, and what we talk about now with an activation energy, this is the minimum amount of energy that the collision must have in order to make products. You can actually and literally think about a reaction as almost like a roller coaster ride. And we all know that if we're not given enough energy to get over the hill, we end up rolling back down. And that's exactly what number 3 here, the collision theory, is talking about. There has to be a specific amount of energy, and that amount of energy changes based on each reaction. That has to be a minimum amount of energy that the collision must have in order to make products. Otherwise, you simply fall back down to reactants. You don't make any products. You have to be given enough energy to actually get over the top of the hill, and then you can actually go make products. So a review here of the collision theory, the basics simply state that, first of all, reactants have to meet. Then they have to meet in the correct way, and finally, they have to meet with enough energy to overcome the activation energy. These are all 3 requirements. Every single one of these has to happen in order to make a reaction. So what I've been told is there are many more collisions between reactants that take place that don't produce products than do. And it's a kind of almost a rare occurrence that a reaction does actually take place. So once again, that's further evidence to show us how many particles are actually in a mole of something, that if the majority of the reactions, or I should say collisions, don't even make a reaction, that just goes to show how many reactants there must be in order for us to actually see a reaction taking place. Okay, now that we've kind of discussed a little bit the collision theory, we can talk about the ways we can manipulate how a reaction takes place in order to increase or decrease the reaction rate. Again, the reaction rate being how fast or how slowly a reaction proceeds. So the first thing we can do to speed up a reaction is we can increase the concentration of one or all of the reactants. And what this does by increasing concentration, what we do is we increase the likelihood that reactants meet other reactants. Okay, so we're making the beaker or wherever we're going to do this reaction, we're making it more crowded, if you will, in terms of the amount of reactants present. And what that will do is that will increase the number of product producing collisions. I want to make sure to be specific here that this does not increase the likelihood or increase the rate at which collisions make products. It simply increases the amount of collisions. And you can think about it as, if there are simply more collisions, there's going to be more reactions. The second thing we can do is we can increase the temperature. And by increasing the temperature, what we're literally doing there, if I can go back to this diagram we had on the last page, we are giving the reactants more and more energy, and the likelihood then that they overcome that activation energy is greater. The third thing we can do is, by physical state, I'm really talking about surface area here. So we can talk about grinding something up. What you're doing is you're exposing more of the surface area. Okay, if we think about a sugar cube, okay, there's a lot of sugar that is, you can almost think of it as buried in the middle of that sugar cube. And if you wanted that to dissolve, and I realize that dissolving is not a chemical reaction, but this serves the purpose here. If I want this to react, the only sugar that's available to react would be the sugar on the outside of the sugar cube. But if we could grind this up, say like powdered sugar, now all that sugar that was on the inside, now that's available to collide, and what we will see is a reaction that is proceeding much faster than if it were simply in this cube shape here. And then finally, the last thing that we can do is we can add a catalyst. There's going to be actually a whole separate video on the process of catalysis, so I'm going to hold off talking about that for now. Okay, so now finally here we are to actually quantifying the rate of a reaction. And the way we do that is with the rate law. So when you hear me describe the rate law, what you need to immediately be thinking of is this general form of an equation right here. And I want to talk a little bit about the features of a rate law first of all. When I talk about the rate right here, that's going to be a number, again with the unit of molarity per second, okay? But that's generally, when I talk about the rate, I'm talking about how fast a reaction proceeds. Once again, it does have the unit of molarity per second. Now on the right side of this equation here, we've got some pretty important stuff. So the first thing is the actual rate constant. That's always going to be symbolized with a lowercase k. It's incredibly important for you to always pay attention to whether or not k is capitalized or lowercase, because the second chapter of this test that we're going to take is going to feature an equilibrium constant, and it is symbolized with a capital K. So it's very important that you always kind of think to yourself whether or not that K is capitalized or it's a lowercase k. K is pretty important, and this will come in another video. The units of K, just as an example, can be used to determine a lot of information about a reaction. So we're going to talk more about K in a later video. But what is most important for this video in terms of this rate law here is the term A raised to the M and B raised to the N. What those are there, those are reactants. Okay, and obviously if we have three reactants, I would need a letter C here and another superscript. But we're going to say in this reaction here that there are two reactants. And what the M and the N represent are what we call the order of reaction. Now, what I mean by order of reaction is simply what we do. Okay, so if we were to change the initial concentration, and before I go any further, square brackets, once again, does mean concentration specifically in the units of molarity. So if we were to alter the concentrations of these, so let's say, for example, that we are going to double the concentration of A. What M tells me is how the rate is going to change. So for example, if M had a value of 1, that tells me that reactant A is a first order reactant. And what you need to know is that means that whatever you do to the concentration of A, the rate is going to mirror that. And this is only for a order of 1. Okay, so what I mean by mirror that is, if you double the concentration of A, the rate will double. If you were to triple the concentration of A, the rate would triple. If you were to quadruple the concentration of A, the rate would quadruple. That's what I mean by mirror, and I think you get the point on a first order reactant. Let's now change the order. Okay, let's make A second order reactant. Now what this means is we're not going to see a mirroring effect here. In fact, we're going to see an exponential increase in the rate once we change M to a 2. So now if we double the concentration of A, and remember A is now a second order reactant, if we double that concentration, we see the rate quadruple. Okay, so whatever this number is, for example, if you were to triple A, we now get the rate increasing by a factor of 9. So we're going to square, if you will, whatever you do to the concentration of A to get our new rate. For the most part, in AP Chemistry, you're going to get 3 orders. You're going to have first order reactants, you can have second order reactants, and you can also have what we call 0th order reactants. There are third order reactants. There's more than that. In fact, there's like 1.5, 1 1/3. So it doesn't always have to be a whole number. So I don't want you leaving this class thinking that first, second, and 0th are the only types of orders. But in terms of what's going to be covered on the AP exam, I'm pretty certain that 0th, first, and second are our only 3 orders that can happen. So let's now change this to a 0th order reactant. Okay. Now A is a 0th order reactant, and when we double A, there is no change to the rate. So a 0th order reactant is a reactant that I say has no bearing. It's not a rate influencing reactant. No matter what you do to it, we will see nothing happen to the rate whatsoever. Okay, so here is a typo in this last bullet point here. That needs to be the word order, not rate. Okay, so there is an overall reaction order, and you can determine that by knowing the exponents and summing them up. So what we can have is we can have the order with respect to a single reactant, and we can have what we call an overall reaction order. So say we were to determine then experimentally, which I'll show you how to do in just a second, that the order of reactant A is a first order reactant and B is a second order reactant. The overall reaction order then would be a third order reaction. So in order to find the overall reaction order, we pretty much do need to know the values of M and N. And the values of M and N can be determined over the course of the next few slides here. Okay, so our second to last slide here is going to discuss what is called the instantaneous rate. What we have here is a graph showing the reaction rate. That green line is the reaction rate over time. Again, I know that because I've got molarity here on the Y. Time on the X, so moles per liter second, is going to be our overall unit here, which again is the unit of the rate of a reaction. What I want you to notice about this is it's not a linear function. It's a logarithmic function. It is actually changing over time. And I do want to talk about the reason why that happens. If you can think about right here at the very beginning, there are all reactants and no products in that beaker. And as we allow them to react, reactants finding reactants is not very difficult for the first part of this graph. But as we go on here, we can see that the rate is starting to slow down. And the reason that that happens is because reactants are struggling to find reactants down here because this beaker is now so product heavy. So the rate is simply the tangent line of this graph right here. And we can see that clearly it has flattened out much more here at the bottom. This reaction rate has slowed down greatly as this reaction has proceeded, and that is because reactants are struggling to find reactants down here. And going all the way back to the basics of kinetics, if collisions can't happen, products can't be formed. So that is in general what we're talking about with this graph here. Now the instantaneous rate, if I can erase some of this here, the instantaneous rate is simply the rate at a specific time and just for an instant, because clearly the rate changes over time. So the instantaneous rate is simply the rate at just one split second over the course of the reaction proceeding here. And the specific type of instantaneous rate is what we're going to talk about now for the last few minutes here of this video. So the initial rate is a type of instantaneous rate. It is an instantaneous rate. It's just the instantaneous rate at the beginning. Okay, so that's what the initial rate is. It is an instantaneous rate. It's the rate at the very beginning once you mix the reactants together and the reaction starts to proceed. It is with this initial rate that's going to allow us to determine the values of the exponents in that rate law that we talked about a few slides back. And we're going to use that method of initial rates in order to do this. So what I'm going to show you now is I'm going to get out of this and get you into some paper right here. I want you to find your books, and I want you to turn to page number 601, and I want you to find question number 33. and we're going to solve this here, and I'm going to show you what the method of initial rates is. So the method of initial rates is essentially a stepwise process in order to determine the value of M and N in our rate law. Okay, and you're going to know very, very quickly when you have to use this method of initial rates, because what you're going to see is a data table. So this is one of the few I guess skills that you're going to have to use on the AP exam, where just the appearance of the problem is going to tell you what you're going to be doing. So anytime you see one of these data tables here, you know you're going to be using the method of initial rates. So in this case here, we've got two different reactants. We've got the hypochlorite ion. Now this is going to be a net ionic reaction, by the way, folks. Only the reactants that take part in the reaction are going to be shown in this table here. And you've got the iodide ion. And so what this table features then will be the concentrations of these reactants, and it also features the initial rate when those specific concentrations of reactants are allowed to react. So what we always want to do first with the method of initial rates is we want to make the generic rate law, but we want to substitute in our reactants. Okay, so no more A and B. We actually know what those reactants are now. So I'm going to write rate equals K times the concentration of the hypochlorite ion times the concentration of the iodide ion. So that's what I call the generic rate law. And a lot of times this is the very first question asked on a free response question if you get a kinetics question on the AP exam. So you get a point simply for changing A into this reactant and B into this reactant. Now you don't want to forget our exponents. And what the method of initial rates is going to allow us to do is we're going to actually determine a numeric value of M and N. So what we want to do now is, if we look at our data table, we have values for this that we can plug in. We have values for this that we can plug in, and values for this. Now, we don't have any values for this, but that doesn't matter, because what we have to realize is that this is a constant. K is a constant. It's never going to change. So if this is never going to change, it's not going to have any bearing whatsoever on any of our math here. So what we want to do with the method of initial rates is we want to pick two different trials where the concentration of one of the reactants does not change. So I'm going to look at trial 1 and trial 2, and the hypochlorite ion, it actually changes, it doubles in fact the concentration, and they hold the concentration of the iodide ion the same. So what I'm going to do is I want to set up basically a system of equations here that's going to mirror this setup right here. And you always want to take the larger rate and you want to put it on top. So again, the easiest way is to actually show you this here. So I'm going to take the rate of trial number 2, which is 2.72 times 10 to the negative 4th equals K times the concentration of the hypochlorite ion raised to the M times the concentration of the iodide ion raised to the N. Now I'm also going to copy down here trial number 1. And we're going to put the rate down here, 1.36 times 10 to the negative 4th. Again, that equals K. Now here's where our concentration of the hypochlorite ion changed, and if you're confused, just follow along here in the book. I'm simply plugging and chugging the information here from the book. And again, they held our iodide ion constant. Now I want to show you what this allows us to do. We are dividing these things. Okay, so we know that K is always the same, so that cancels. This is identical, so that cancels. So what this basically allows us to do now is we can divide the numbers that have changed. So what we get is when we divide these two here, and if you can't realize this or if you can't see this, go ahead and throw this into your calculator. You're going to realize that those this divides into this to get the answer of 2 here. And this is also doubled, but remember that's raised to the M. Now what we can realize now is, or we can ask ourselves, what does 2 raised to in order to still equal 2? In other words, what could be placed for the value of m right here in order to remain or have 2 remain the same? And hopefully we realize that that is a 1. Okay, so now going back to our generic rate law, I now know the value of m. And I have to do this one more time to find the value of n. So what I'm going to do is I'm going to erase all of this, and we're going to find 2 sets of trials where this time the concentration of the hypochlorite ion stays constant, but we change the concentration of the iodide ion. And if we look, that happens in trial 1 and trial 3. Okay, and again, trial 3 has the larger rate, so I'm going to put trial 3 on top because we do want this to be whole numbers. It'll still work if you put the smaller trial on top, but sometimes dealing with fractions and exponents, it's a little tough. So looks like, folks, this is going to be an exact copy of what happened earlier, and that's okay. A lot of times this will change. Also, a lot of times you're going to really need your calculator for these because it's not quite as obvious to see. Now we do know the value of m now, so I'm going to put that in there. But then the value of the iodide ion here is going to be here. Okay, and again, this is the exact same copy of the previous problem here where we were finding the order of the hypochlorite ion. That doesn't change. This did. Okay, so when we go to divide, once again we get 2. Those cancel, 2 equals 2 to the n, and what we get is a value of n equals 1. Now, when we discuss this in class, we're not actually done with this yet, but this is the basics here. We're going to do a few of these in class, but there are other things we can do. For example, finding the value of the rate constant. We'll also find the overall order by adding up the sum of the exponents here, but more of that we'll talk about in class tomorrow, and that's where we'll stop.